How's it going, ladies and gentlemen? Mr. Donahue here, looking at some 10.5 further applications of the ideal gas equation problem. So it has to do with the ideal gas law and applying it maybe with some other equations, some other concepts, kind of, get more out of it. So, for example, first one, if we're looking at 18, it says the volume of a sample of gas, and then give you the grams, was 752 milliliters at this pressure and temperature. The gas is blank. Really? We can figure out which gas it is just based on that? Absolutely. And the trick is going to be, we're going to compare the GFMs, the gram formula masses of these, because that's different between all of them. And based on the information they gave us, we can figure it out. So the first step is to figure out what gas do we have. So we're going to use the PV equals nRT equation. We're going to rearrange it so that we get moles by itself, right? And the second thing that we're going to have to incorporate is, all right, well, they give us grams. So how do we go from grams to GFM and all that stuff? Well, we have a second equation for moles. It's the same thing as grams over GFM, isn't it? All right, well, instead of dealing with some ugly numbers, how about we just combine these equations, right? With moles equals PV over RT, they also has to equal grams over GFM. So I'm just going to substitute that in up here. So we got grams over GFM equals PV over RT. Now, the thing we're trying to solve for is the GFM. So, how do I get it by itself? All right, it's this little thing, you might have heard of it. It's called algebra. So I'm going to rearrange stuff, and I'm going to do it in one foul swoop. Watch. All right, or maybe two foul swoops. Grams is going to go down over here, and I'm left with 1 over GFM, and I'll just take the reciprocal of that, flip it, and I'll get the GFM equals grams times RT over P times V. And now I got one equation, and I just plug in everything. 2.49 grams, right, times R, which R am I using? The 0.08206, because I got atmospheres over here, times T, which has got to be in Kelvin. So what do I get when I do that? 335 Kelvin, all over the pressure, 1.98, times the volume in liters, 0.752. And I should get the answer of D. Should get a GFM of 46.0 grams per mole. Which, all right, well, which one of these things has that GFM? D. D does, NO2. All right, 19. The density of blank is 0.9 grams per liter at STP. All right, so let's take a look at our ideal gas equation. And we want density. All right, well, what do we know about density? It'll be grams over liter, right? Mass over volume. Interesting. So I have a density equation and I have an ideal gas equation, and no common terms. So, well, except for volume, right? So what am I going to do with this? What you're going to do is you're also going to go, hey, well, I know that N, I know moles equals grams over GFM, isn't it? So why don't I substitute that in and get a slightly different equation? But the same thing, really. It's grams over GFM. Right? Perfect. Now I need to get it to look like this. Density. I need grams over liters. Well, my liters would be my volume. So how do I get grams over liters? How do I rearrange this? Well, first, grams is on top on this side. So why don't I divide volume on both sides? And now I got to get rid of everything that isn't grams over liter. Right? Oh, can I finish getting rid of that? All right, so I got to divide this side by RT. I got to times it by GFM. And now I've moved everything. Just a little algebra. I'm going to make that a bigger gram. So now I got, remember the volume is going to be in liters. So now I've just rearranged it so that I have my density, right? All right, so now which one of these things is going to give me that density? Well, now I just plug and chug, right? I'm looking for a 0.9 density. Probably be easier just to go backwards, isn't it? So I go, all right, well, if I'm GFM times the pressure at STP, 1 atmosphere, over 0.08206 for the R times T, which is 273 at STP, has to equal 0.9, all right, 0. So now you just solve for the GFM, and you're going to find it to be the same as neons. All right, you're going to get a GFM of 20.2. I know, right? What, Mr. Johnny, can you do that again? No, but you can pause it and rewind it and look at the beauty that is algebra. All right, 20. Another density question. So why don't I just cheat and use the equation that I figured out before? It's got to be equal to the pressure times GFM over RT. All right, I already solved it once. So I can just go back and consult it. It says the density of NO2 in a 4.5 liter tank at that pressure and that temperature is blank. All right, so well, we know the GFM of NO2 because we can figure that out. And looking at my notes, it looks like I found it to be 46.0. 4.5 liters we just take, 760 torr we take. This we got to convert to 298 Kelvin. So now it's just 760 times 46 over the R that uses torr, which is 62.36, times the temperature, 298. And we get 1.88 grams per liter. 21. Molecular weight of the gas is blank grams per mole if 6.7 grams of the gas occupies 6.3 liters at STP. All right, so we can still, again, use that density equation. So we know density equals P times the GFM all over R times T. And I want the molecular weight. So we're looking for GFM. So why don't I just rearrange that to get GFM by itself through the powers of algebra. Ta-da! All right, well now let's figure it out. Sorry guys, I'm having a brain fart at the moment. All right. Oh, no, we don't even need to, yeah, I guess that's the same thing, huh? So the density, they don't tell us directly, but they give us grams and they give us liters. So we just do 6.7 over 6.3. That's our density times our R. You know, you pick which R you want to use. I personally am in favor of this one with atmospheres times the temperature, which is 273 at STP, right? STP up here, all over the pressure, which at STP would be 1 atmosphere. So now I plug and chug, and I get my GFM to be about 23.8-ish, which would become 24, choice A. The volume of the hydrogen gas at 38 Celsius and 760 torr that can be produced by the reaction of 4.33 grams of zinc and excess sulfuric acid is blank. All right, so let's figure out what is that equation. So we got zinc reacting with hydrochloric acid, right? And it's saying, what is the volume of gas? Well, I know I'm going to get H2 gas. And I'm going to get, well, what compound is that going to be? Zinc's +2, chlorine's -1, so ZnCl2. So I got to balance it. Pretty easy one to balance. Watch and learn. Oh my God, look at that. 2 hydrogens on the right. Now I got 2 hydrogens on the left. 2 chlorines on the left, 2 chlorines on the right, 1 zinc, and 1 zinc. So it's all balanced now, nice and pretty. So now I can start looking at the numbers. It says I used 4.33 grams of zinc. Well, grams isn't helpful. I got to convert that to moles by dividing by the GFM, which is 65.4. So divide by 65.4, and I get 0.066 moles of zinc, of just zinc. So now I got to look at, well, what's the gas? Well, it's hydrogen gas, so I got to look at the ratio. Fortunately, it's an easy one. It's a 1-to-1 ratio. So if I have 0.66 moles of zinc, I'm making 0.066 moles of H2. So now they're asking for liters, and this is where the ideal gas law come into play. So we rearrange it, we get volume equals nRT over P. Now we just plug and chug. All right, they're using torr, so we want to use the 62.36 R. What's the temperature in Kelvin? 311 Kelvin. And divide by the pressure, which they give us a 763. And that will equal 1.68. It sure does. 23. I like this one because it's applicable to real life and stuff, and that's not so abstract. And it's like, hey, we use this in airbags and it saves people's lives. And this is the reaction, right? So it decomposes sodium azide, which is this stuff, as a source for rapid inflation because it makes that much gas. So it's a reaction where gas is a product. And wants to know, what is the mass of NaN3 required to provide 40 liters of N2 at this temperature and pressure? All right, so first thing that we're going to have to do is we're going to have to figure out, well, how many moles of gas is that, right? First step, moles of N2. How do we, what is that? And then from there, we can do some stoich to figure out moles of NaN3. And it wants it in mass. So then the next step would be to go from moles to grams. All right, so I'm going to erase these because I need room to work. All right, so first step is we're going to use the ideal gas equation. Moles equals PV over RT. That will give us moles of N2. So I plug and chug, and I'm not bothering with that step because I've done it a million times for you already. So we get that many moles of N2. Next step is, all right, we'll look at the ratio between N2 and NaN3, sodium azide. It's a 2-to-3 ratio. And this 1.64 is our 3, right? That is on this side. So you solve for x, do a little cross multiply and divide. You get x equals 1.09 moles of NaN3. So now it wants it in grams, so we just simply times by the GFM, which I found to be 65 grams per mole, and you get 71.1 grams, which would be choice D, as in David. All right, kind of a difficult problem, but just, step back, think about what's going on, get the big picture, and then just go, get your plan and go for it. All right, so I hope you found that helpful. Bring questions to class. I'll see you there.